We saw that if we try to realize a common source amplifier with a very high gain, we also need to increase the power supply, and for very large gain values this power supply reaches unreasonably large levels and we won't be able to realize that. We'll see how to modify the common source amplifier so that we can implement large gains with reasonably small power supplies. Now again, I won't show all the details of the bias. I'll show only the transistor and the resistor. I'll assume that the gate is biased at a voltage VG0. So the source gate voltage at the operating point is VDD minus VG0. And across the load resistance, the operating point voltage is ID times RL. Then we apply an incremental voltage Vi here, and at the output we get an incremental voltage minus GMRL times Vi. Now let me draw the operating point and the incremental pictures separately. So this is the total picture. This shows only the operating point. And if I draw only the incremental picture, we know that the incremental equivalent of the MOS transistor in its simplest form is just a voltage controlled current source, GM times, if this is VGS, GM times VGS, and the incremental equivalent of the resistor is just a resistor. Okay, and at the output we would get minus GM RL times Vi. So this is the incremental signal picture. Now just to recap the problem we had, if we try to increase the gain, we have to increase RL. Let's say that's how we try to increase the gain. Then the current that is flowing through the MOS transistor will flow through a bigger resistor and create a larger voltage drop, which means we have to increase the supply voltage. Okay. At the same time, we know that the gain is proportional to RL. So RL has to be large in order to realize a high gain. So the problem is, if we try to increase RL to realize a larger gain, the DC drop also increases. And this load RL that we are using, it's a linear element. So in the incremental picture and in the total picture, it is exactly the same. Okay. So now let's look at this graphically. Let's look at the IV characteristics of RL. I'll show only in one of the quadrants. IV characteristics of RL. It's like this. I equals V by RL. And if I have a larger resistor, the picture looks like this. Now let's say the MOS transistor is biased at a certain ID. We want to get a certain GM, and that gives us the value of ID at which to bias. If we have this resistor shown in black, then the operating point voltage VRL across the resistor would be over there. And if we have a larger resistor, it will be over here. This will be the drop across the resistor. Now the gain of the amplifier is related to the slope. This you know. Basically the incremental picture is related to the slope of the IV characteristic. So the gain of this amplifier is related to the slope over here if we use this particular value of RL. And it will be related to the slope at this point, at the operating point, if we use a larger resistor. Okay, so I versus V slope becomes smaller if we use a larger resistor. Now what we want is to combine a smaller voltage drop, something like this, with a smaller slope. So that means we have to have a characteristic that passes through this point corresponding to the smaller voltage drop, right? This is the but also combine it with the smaller slope. So that means we need a characteristic that's like that. Okay, so it has to pass through this point for a small VRL, and it has to have a small slope. And it's very clear that this is not a linear element, because if it's like this, its characteristic cannot pass through the origin. Okay, whereas these two, their characteristics do pass through the origin, because once we specify this point, we cannot specify the slope independently. To have it pass through the origin, we just have to draw this black line. Okay, whereas if we do have a nonlinear element, it's possible to pass through this point corresponding to a small VRL and also have a small slope. Okay, so at the operating point, the characteristic should look like this. Okay, now what is an element that we can replace the resistor with and whose characteristic is like this? We already know this element and we are very familiar with it, and it will become more obvious if I complete the characteristics. First of all, remember that the characteristics have to look like this at the operating point. Outside of this, it can look anything, right? Because the small signal gain only depends on the slope at the operating point. So let's see a possible extension like this. Okay, so the characteristic bends down and goes to the origin for small values of V. For 0V, the I is 0, and then it goes like this. And we are of course already familiar with this characteristic. What is this after all? This is the ID VDS characteristic of an NMOS transistor for a given VGS. For a certain VGS, initially for small values of VDS, this will be VDS now, and this will be ID. It is in triode region up to this point, and after that it will be in saturation region. Now the slope in saturation region depends on the value of lambda, as you know. Okay, all we have to do is to replace the resistor by an NMOS transistor which is biased in saturation region. Okay, that is very important. We have to make sure that the NMOS transistor is biased in saturation region. We will see how to do that. We will have the PMOS device as before, no change here. The gate is biased at certain VG0, and instead of a resistor here, we will use a we'll use an NMOS transistor. Now because we have two transistors, let me call this VGP and I'll bias this at VGN. The source gate voltage of the PMOS transistor is VDD minus VGP, and the gate source voltage of the NMOS transistor is VGN. Okay, we'll see how to adjust this later. And the output is taken here. The output is at some operating point VO bias. We'll see how to find this. And if we apply an incremental voltage Vi, we'll have an incremental voltage VO at the output. Now let's look at the operating point picture first. So all I have to do is to remove the incremental parts. Now how do we find out what the value of VO bias is? One of the ways of solving for voltages and currents in a nonlinear circuit that has only two constraints is to do it graphically. It also gives a good visualization of what happens. So first we draw the characteristic of M1, the PMOS. Let me draw it in a different color. Okay. Now the axis I choose are basically this current I and this voltage V. Okay. Now for the PMOS transistor, the source drain voltage is VDD minus V, where V is the variable I choose for drawing the graph. This is I, this is V, this is VDD minus V. Okay, and the source gate voltage is some fixed value, it is VDD minus VGP. Now, how does the characteristic of the PMOS look like on this axis? So it's quite easy to draw, but the first time around, let's draw it on the conventional axis, which is on ID of the PMOS transistor versus VSD of the PMOS transistor. Let's draw this. This is of course the familiar MOS transistor characteristic. It will be like this with a small slope. This is the boundary between saturation and triode region, and that voltage is given by VDD minus VGP, which is the source gate voltage minus the threshold voltage of the PMOS transistor. Okay. Now how do I draw it on this IV axis? This I is nothing but ID of the PMOS transistor. We know that by convention we take the current of the PMOS transistor coming out of the drain. So this I is nothing but ID of the PMOS transistor, whereas this V is VDD minus VSD of the PMOS, right? Because VSD of the PMOS transistor is given by VDD minus V. So all that happens is that we have to plot the same curve as this, but on an x-axis which is redefined, it's VDD minus VSD of PMOS. So it's quite easy. So the point VSD equal to 0 here corresponds to V equals VDD. Okay, and similarly as we increase VSD, we have to fall down from VDD. So the characteristic looks like this. Okay, and this point here at V equal to 0, this corresponds to VSD equals VDD. So all we have to do is to flip this characteristics around so that 0 becomes VDD and VDD becomes 0. That's all. And this point would be basically VGP plus VTP. It is equal to VDD minus this point. Okay. Now on this, let's superimpose the characteristics of the NMOS transistor. This is quite easy. The I and V that are marked here, which I have chosen as variables, are the same as ID and VDS of the NMOS transistor for a given VGN. Okay. So what will that look like? It is the conventional NMOS transistor characteristics. This is for NMOS and this is for PMOS, and for a particular source gate voltage, VSG equals VDD minus VGP, and this is for VGS equals VGN. Okay. The point of intersection of these two curves is the operating point. This is VO bias, and as the input changes, if there is an increment Vi that is applied, we can get what happens by looking at the incremental picture. And that's again simple. In the incremental picture, we have only the incremental voltage Vi. The incremental picture of the PMOS transistor is like this. It is GMP times VGSP. We have to distinguish between the two transistors. That's why I do this. And it also has its output conductance. Sometimes we neglect this output conductance, but in this case it is necessary. So this is the GDS of the PMOS transistor. The incremental equivalent of the NMOS transistor, what is it? It is GMN times VGSN, where VGSN is the incremental voltage between the gate and source of the NMOS transistor. Now this VGN, this is a fixed bias voltage. Okay, so this is VGN. So the incremental voltage here is 0. Okay, so this is really incrementally grounded. So this current source is not in the picture at all, and all we have is the incremental output conductance of the NMOS transistor. Okay, and this voltage here is the incremental output voltage. Okay, so now see what happens. The gain V0 by Vi is given by minus Gm times the effective load resistance. What is the load resistance? It is output resistance of the PMOS in parallel with the output resistance of NMOS, or in other words, it's the reciprocal of the sum of these two output conductances. Okay, so this is the gain of the amplifier now. If both transistors are in saturation, then GDSP and GDSN will be much smaller than GMP, and the gain that is realized will be very large. In this case, the gain value has no relationship to the voltage drop across the load. This is the load. We have the DC drop across the load. The gain is not related to this. The gain is related to GM and GDS. And you can make GDS very small by choosing a transistor with a small lambda. Okay. Whereas this voltage is not related to that. Okay. So this is how we realize a very large gain. And this is a very common way of doing that. We need very large gains while realizing any negative feedback circuit. And in this case, instead of using a resistance as a load, we use a MOS transistor as a load. Okay. So that's why this circuit is known as an active load circuit, or this MOS transistor here is the active load. Okay. We refer to transistors as active devices. I think you already know that they are not active in their total picture. They are passive because they draw power, but incrementally they can look like active devices. And frequently we use the output conductance of a transistor as a very large resistance which can be used as a load. Okay. Now the special feature of this very large resistance, the output conductance of a transistor, is that the voltage drop across the transistor is not related to the current flowing through it. In a linear resistor, the voltage drop is proportional to the current. It is current times the resistance. Here there is no such direct relationship. All we want is for the transistor to remain in saturation region. So for that we have to maintain a certain minimum voltage across the transistor, but that's not related to the value of the resistance, which is the incremental resistance of the MOS transistor. Okay, which is the incremental output resistance of the MOS transistor. Okay, we'll see many variants of this and also how to bias it reliably in the following lessons. There are many variants of this. We also need to come up with a robust arrangement to bias this properly. Okay, because right now I have assumed that these two curves intersect where both transistors are in saturation region. There has to be some way of guaranteeing that. Okay.